Pick up anything, a book, a coffee mug, your own phone. You feel weight. And instinctively, you believe you are feeling the amount of stuff inside it, the material it is made of, the atoms, the molecules, the physical substance. Your hand says this thing is heavy because there is more of it. Here is what quantum physics has revealed. The vast majority of that weight has nothing to do with the physical stuff. When physicists cracked open the proton, the particle that makes up nearly all the visible matter in your body, they found something that defies everyday intuition. The 3 tiny quarks rattling around inside any proton account for less than 1% of its mass. Less than 1%. The other 99% comes from something that is not matter at all. It comes from energy. Pure energy trapped inside an invisible field by the strongest force in nature, the strong force, the same force that holds the nuclei of every atom in your body together. Tonight, we are going to find out what mass actually is, and we are going to find out why that same energy, that same ghostly field, is the exact reason matter falls. The reason your feet stay planted on the ground. The reason a black hole can bend light around itself. Mass and gravity are not 2 separate mysteries. They are 2 faces of the same coin, and once you see how that coin is minted, you will not look at the physical world the same way again. If you are the kind of person who likes having your picture of reality quietly rearranged, do me a small favor before we go any further. Tap the like button. It costs nothing, and it tells the algorithm that this kind of deep exploration deserves more reach. And if you have not yet, subscribing is the simplest way to make sure the next one finds you. Now, back to the question. Let us take you back to a moment almost 120 years ago, because the answer we are chasing has a strange history. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published 4 papers that would dismantle physics and rebuild it from the floor up. One of them, the one we now call E equals mc squared, said something almost absurd for its time. Energy and mass are the same thing. They are convertible, they are interchangeable, they are just 2 ways of measuring the same quantity in the universe. A hot cup of tea weighs more than a cold one. A wound-up spring weighs more than a relaxed spring. The difference is absurdly tiny. You would never feel it, but it is real. You can do the sum yourself. 1 calorie of heat energy, the kind of energy a single almond contains, weighs, if you converted every drop of it to mass, about 46 trillionths of a gram. The number sounds microscopic. It is, but it is not 0. That equation is the seed of almost everything we're going to talk about tonight. Because if mass and energy are the same thing, then the question, where does mass come from, quietly transforms itself into a different question. Where does energy come from? Why does anything have energy at all? And once we have answered that, the question of why things fall, why gravity exists at all, gets very close to an answer that Einstein spent 10 years finding. Now, gravity had its own origin story, and it is worth dwelling on for 1 minute because it sets up the shock that is coming. Isaac Newton sat in a garden. Or rather, the legend says he sat in a garden, although most historians now think the garden story is apocryphal. Whether or not an apple physically struck his skull, the realization did hit him. The same force that pulls an apple from a branch keeps the moon in orbit around the Earth, and the Earth in orbit around the sun. There is one universal law, one equation. F equals g times m1 times m2 over r squared. Force equals the universal gravitational constant times the first mass times the second mass divided by the square of the distance between their centers. Beautiful, compact, capable of explaining the rising and falling of tides, the orbit of every planet in the solar system, the precise return of Halley's Comet every 75 years. For 240 years, that equation was treated almost as scripture. By 1846, the British mathematician John Couch Adams and the Frenchman Urbain Le Verrier independently used the same equation to predict the existence of a planet nobody had ever seen, Neptune, before Johann Galle at the Berlin Observatory pointed a telescope at the spot they had calculated and found it. The Newtonian gravitational law had earned its keep. But there was one strange and uncomfortable assumption buried inside it, and it had bothered some of Newton's greatest contemporaries. The equation said that when the sun pulls on the Earth, that pull is instantaneous. The Earth feels the sun's gravity at the exact moment the sun exerts it. No delay, no travel time, no carrier. As if two objects on opposite ends of the universe were connected by an invisible elastic band that snapped taut the moment either of them moved. Christian Huygens himself, who had worked out the wave theory of light, refused to use Newton's gravitation because he found instantaneous action at a distance philosophically repugnant. Gottfried Wilhelm Leibniz, Newton's great rival, called the attraction a perpetual miracle. Georges Louis Leclerc, the Comte de Buffon, suggested that all of Newton's physics was simply a convenient summary of appearances, not a description of underlying reality. In 1784, the Swiss physicist Georges Louis Lesage proposed the first concrete mechanical alternative. He suggested that space was filled with tiny, ultra-mundane corpuscles, streaming in every direction. Each one bumped into ordinary matter constantly. Two massive objects close to each other would mutually shield each other from some of those corpuscles on the sides facing one another, leaving a net push from the outside, which would appear as attraction from across a distance. The mechanism was wrong in detail and calculated in a way that would cool the sun far too quickly, but it was the first serious attempt to give gravity a carrier. Through the 19th century, attempts to find the carrier, often called the ether or the luminiferous medium, dominated theoretical physics. Augustin Jean Fresnel, James Clerk Maxwell, Hendrik Lorentz, every one of them tried. None succeeded. Einstein's radical move in 1915 was not to find the carrier. It was to delete the question entirely. Let us actually go inside an atom. Take a single hydrogen atom, the simplest one, a proton in the middle, and an electron somewhere out around it. Everyone has seen the textbook image, a little solar system with a nucleus in the middle and electrons on neat orbits. Forget that image. It is so simplified that it is almost a lie. The electron is not orbiting like a planet. It exists as a fuzzy cloud of probability, and the proton at the center, that tiny dense dot that every textbook shows you as a single ball, is itself a chaos. Inside the proton there are 3 valence quarks, 2 up quarks, and 1 down quark in the case of a proton. They are moving at relativistic speeds. They are constantly emitting and absorbing other particles called gluons, and the gluons are themselves doing the same thing. Every microsecond, the inside of your proton is a screaming storm of energy, creation, annihilation, and exchange. It is not at all like a marble. It is like a contained hurricane. Here is the thing nobody tells you when you first learn this. Everyone walks away with the impression that quarks give a proton its mass, because the textbooks list quark masses, and because there is a famous boson called the Higgs that supposedly gives things mass, and so the picture students carry around is that the quarks are the main ingredient. They are not. They are an ingredient. They are a vanishingly small ingredient. Hold this thought. The strongest force in nature, by the way, makes sense if you think of it as the glue holding together the tiniest bits of matter, but the comparison neglects just how strongly it actually pulls. The strong force, mediated by the gluon field, is roughly 100 times stronger than the electromagnetic force that holds electrons to nuclei, 10,000 times stronger than the weak force that drives radioactive decay, something like 10 to the 38 times stronger than gravity. You read that right. A single proton's internal gluon forces are stronger than the entire gravitational pull of the Earth on itself, by 38 orders of magnitude. Gravity is absurdly weak. It is the weakest force by an almost incomprehensible margin, which is why you can lift a coffee cup off the floor with your hand, but you cannot lift a coffee cup out of a black hole. The strong force is on the inside of the cup, holding its protons together. Gravity is on the outside, asking the cup to fall. They are playing completely different games. Now, before you reach inward and try to weigh those 3 quarks, try to add up their masses, you run into the surprise. The top quark weighs about 173 gigaelectron volts, but it is not in the proton. The bottom quark weighs about 4, but it is not in the proton either. The up quark and the down quark, the two that actually live inside a proton for most of its life, are absurdly light. The up quark weighs roughly 2.5 megaelectron volts. The down quark weighs roughly 5. Add them all up, and the total quark mass inside one proton is about 9 megaelectron volts. The proton itself, when measured, weighs about 938 megaelectron volts. So the quarks, those tiny points you have been told make up mass, contribute roughly 1% of the proton's actual mass. Where does the rest come from? This is the puzzle that took physics half a century to crack open, and the answer lives inside a field you have probably never heard of. The gluon field, the strong force field. The carrier of one of the 4 fundamental interactions of nature, the gluon field is everywhere inside hadrons, particles made of quarks, and it is violent. It carries one of the strangest properties of any known physics, a property physicists call color charge. It has nothing to do with visible color. It is just a label, a useful name for a quantum number that comes in 3 varieties and forces the gluons to behave in bizarre ways. To picture what is happening at the scale of 1/10,000,000th of a centimeter, imagine shrinking yourself down to the size of about 1 femtometer, the official diameter of a proton. You are now standing inside a city that is about the size of a small room in a suburban house, but it pulses with more energy every second than a major power plant does in a year. Look up. There are 3 bright objects, the valence quarks, moving at relativistic speeds. They are never at rest. They are never in one place. They are surrounded by a dense, shimmering haze of gluons. Every gluon briefly transmutes into a quark-antiquark pair, which annihilates back into gluons, all within a tiny fraction of a femtosecond. The air in this room, if you can call it air, is itself a gluon field, alive with energy. If you try to walk toward the boundary of this city, you will be pulled back with greater and greater force. That force is not like a wall. It is more like an elastic lacework of stretched energy threads, the flux tubes of the gluon field, growing stiffer the further you pull them. The lacework refuses to break. It will, at the limit of its stretch, create an entirely new pair of quark and antiquark by drawing on vacuum energy to satisfy its own continuity. That is confinement. You simply cannot leave the proton. The gluon field will not allow it. Every kilogram of mass near you, in this imagined city, is gluon field energy stored in this cramped, hyperactive space. The most important bizarre thing about the gluon field is that it gets stronger as you pull its particles apart. This is the opposite of gravity. Gravity gets weaker with distance. The strong force gets stronger. If you try to separate 2 quarks, the energy in the field between them rises so steeply that it becomes more efficient in pure energy terms to just spawn a new quark-antiquark pair out of the vacuum than to keep pulling. The field refuses to let its quarks go. Physicists gave this refusal a name: confinement. To picture this further, imagine trying to pull apart 2 magnets that get stronger the further you stretch them. Imagine the snap getting more violent the more you fight it. At some point, instead of one thin connection snapping, the energy becomes so great that it is cheaper for the vacuum to just create 2 new magnets with their own stretch connections than to break the original one. That is what is happening inside a proton, except the energy gradients are more extreme than anything in the everyday world. In 1973, 3 young theorists, David Gross and Frank Wilczek at Princeton, and independently David Politzer at Harvard, realized that the strong force gets weaker at very short distances under certain conditions. The closer quarks get to each other, the more freely they move. The further apart they get, the stronger the force becomes. They called the discovery asymptotic freedom. All 3 shared the Nobel Prize in 2004. And here is the part that changes everything. The energy stored in that gluon field, the energy locked up by confinement, by the constant exchange of gluons between the quarks, by the violent churn happening at light speed inside every proton, that energy has mass. Because of E equals AOSE squared. Energy is mass. The gluon field energy is roughly 99% of what we call the proton's mass. Let that land. When you pick up a coffee cup, when you feel your own weight on a bathroom scale, when you stand on a planet and feel pull, that weight, is not coming from the stuff inside the atoms. It is coming from the energy of invisible fields. The proton is mostly empty of mass, it is mostly energy, and that energy has weight because energy equals mass. Now that 99% is not a small curiosity. It is the entire reason a star can shine. When hydrogen fuses into helium inside the core of a star, the resulting helium nucleus is slightly lighter than the hydrogen nuclei that made it. Where did the missing mass go? It went into energy. That energy pours out as light, as heat, as radiation. The mass discrepancy, roughly 0.7% of the rest mass per fusion event, is exactly the energy budget of every star ever born. If protons were made of stuff, that magic would not work. If protons were made of pure quark matter, fusion would release a tiny fraction of what it actually does, and stars would barely glow. The gluon field, locked away inside every proton of every star, is doing the work of the universe. How do we know this with certainty rather than as theory? In the late 1960s, physicists at the Stanford Linear Accelerator Center, SLAC, fired high-energy electrons at protons and watched how those electrons scattered. Jerome Friedman, Henry Kendall, and Richard Taylor led that program. They expected to see the electrons bounce off a few hard, dense quark-like points inside the proton, the way bullets scatter off ball bearings in a sack. They did see that. But they also saw the energy distribution inside the proton include a major component that was not behaving like individual quarks. Something else was carrying momentum and energy inside the proton. Slowly, painfully, over a full decade, physicists realized what that extra component was. Gluons. The thing holding the quarks together was itself a measurable carrier of energy, scattering the electrons through a process called deep inelastic scattering. Friedman, Kendall, and Taylor won the Nobel Prize in 1990 for that work. Then in November 1974, a particle was discovered almost simultaneously at Brookhaven National Laboratory on Long Island and at the Stanford Linear Accelerator Center. The particle was named J by one team, named psi by the other, and so today it is referred to as the J/psi particle. The J/psi turned out to be a bound state of a charm quark and an anti-charm quark. Its discovery, known as the November Revolution, opened a new era in particle physics because it confirmed that quarks existed as real objects inside hadrons, confirmed the framework of quantum chromodynamics, QCD, on a single experimental observation. Burton Richter at SLAC and Samuel Ting at Brookhaven shared the 1976 Nobel Prize for that work. Put those results on top of SLAC's earlier deep inelastic scattering experiments, and the gluon field is not speculation. It is the best measured dynamical system in modern physics. The gluon field's energy contribution to the proton has been measured, fit to theoretical predictions, and the agreement between the numbers is to 4 decimal places. Quantum chromodynamics is one of the most rigorously tested theories in human history. But there was a second, completely independent proof that gluon field energy inside stars was the source of their light. The sun is powered by hydrogen fusion. The dominant branch of that fusion produces, as a byproduct, a brand of elementary particle called a neutrino. Neutrinos are the ghosts of the particle zoo. They have no electric charge, almost no mass, and they barely interact with anything. A neutrino can pass through a light year of lead without slowing down. They are exactly the kind of particle you would expect from a fusion process happening inside an extraordinarily dense star. Physicists started counting solar neutrinos in the late 1960s using a vast tank of cleaning fluid buried deep in the Homestake Mine in South Dakota. Raymond Davis ran the experiment. What he found kept physicists awake for 30 years. He detected only about 1/3 the number of neutrinos that the standard solar model predicted. Where were the other 2/3? There were 2 possibilities. Either our model of the sun was wrong, in which case our assumption that gluon field energy powers stars was wrong, or our model of the neutrino was wrong, that is, neutrinos were doing something funny on their way out of the sun and to the detector. In 2002, the Sudbury Neutrino Observatory, SNO, in Canada solved the puzzle. The SNO detector could count both the electron neutrinos that earlier experiments had counted, and a separate flavor of neutrino called the muon or tau neutrino, produced by the same fusion reactions in the sun, but converted during transit by a strange effect called neutrino oscillation. When SNO added up the counts of every flavor, the total matched the standard solar model exactly. The sun was not wrong. The neutrinos were simply changing identity on the way out. The work earned Art McDonald the 2015 Nobel Prize, and the implication for tonight is crisp. The energy budget of our sun, the basic equation of why stars shine, is precisely the gluon field energy missing from helium mass and showing up as sunlight. We now know this in two independent ways, from two independent instruments, decades apart. Now consider what happens to that gluon field energy when matter is crushed. A neutron star is what remains when a star roughly 8 to 20 times the mass of our sun collapses at the end of its life. The outer layers are blown off in a supernova. The core, a mass around 1.5 times the mass of the sun, somehow squeezes itself into a sphere roughly 12 kilometers in diameter, smaller than many cities on Earth. The density climbs to something like 700 trillion kilograms per cubic meter, higher than the density of an atomic nucleus by some measures. Inside a neutron star, protons and electrons have fused into neutrons. The neutrons themselves are again 99% gluon field energy. So a neutron star is essentially a giant fusion-powered lump of gluon field energy compressed to absurd densities. But here is the kicker. So much energy is being locked up in the gravitational field of the neutron star itself, in its curvature, that the gravitational binding energy subtracts significantly from the total rest mass energy you would measure from the outside. How significant? For a neutron star of 1.5 solar masses, the gravitational binding energy is roughly 20% of the rest mass energy of the constituents. That means if you somehow disassembled the neutron star and weighed every neutron individually, then compared that sum to the mass of the intact neutron star measured from outside, the intact neutron star would be lighter by about 20%. That missing mass is not really missing. It is the energy cost of holding the star together against the curvature of its own spacetime. The same gluon field energy you have been hearing about, doing its job, now also keeping a ball of nuclear matter from collapsing, while simultaneously the curvature it creates works as the price tag. A kilogram of neutron star matter is not a kilogram of coffee cup matter. The arithmetic of E equals mc squared, when it is stretched to this scale, becomes astronomical. So the gluon field is the answer to where most of mass comes from. But now we need to ask the next question. Where does the 1% come from? Where do the quarks get their tiny mass from? What gives a single quark its own weight? This is where the Higgs field enters. And this is also where 99% of public explanations go catastrophically wrong. The Higgs boson, the particle discovered at the Large Hadron Collider in 2012, the one that made headlines worldwide, did not give you most of your mass. It gives quarks their intrinsic mass. Those tiny individual quark masses, 2.5 megaelectronvolts for the up, 5 for the down, 0.5 for the electron, come from the Higgs field. But that is 1% of the proton's total. 1%. Headlines, news segments, even textbooks often say, the Higgs is what gives you mass. They are, technically, 3/4 wrong. The Higgs gives fundamental particles a tiny fraction of their eventual bulk. The gluon field does the rest. So what is the Higgs field? It is a field that permeates all of space, every part of the universe. Empty space, deep space, the space inside your hand right now, all of it. The Higgs field has a non-zero value even when it is at its lowest energy state. Physicists call that the vacuum expectation value, sometimes shortened to VeV. Its value is about 246 giga-electron-volts. That number is not arbitrary. It is directly measured from the way the W and Z bosons interact with one another, and it sets the scale for every particle mass the standard model can predict. Now, when a particle like an electron or a quark moves through this field, it interacts with it. The interaction is a kind of drag. The particle walks through a sort of cosmic molasses, and the strength of its coupling to that molasses, how sticky the molasses is for that particular particle, sets its intrinsic mass. The top quark has an enormous coupling to the Higgs field, and so weighs 173 giga-electron-volts basically on its own. The up quark barely interacts and weighs almost nothing. Photons do not interact at all with the Higgs field, and so have zero intrinsic mass. That is why they travel at the speed of light. Here is a useful comparison to keep the magnitudes straight. The top quark, with its enormous Higgs coupling, is about 340,000 times heavier than the up quark inside your protons. It is also about 350,000 times heavier than the electron. The reason the top quark is so heavy, in this picture, is that it is fabulously sticky in the cosmic molasses of the Higgs field, walking through it as if through wet cement. The electron pushes its way through like a kid through a swimming pool, slowing almost not at all. The top quark stumbles and wades. This is the source of a popular metaphor you have probably heard. The Higgs field is like a thick soup. The particles move through it at different rates depending on how sticky the soup is for them. It is a useful image, but it has a major flaw, and this is the only place I will set you straight on the metaphor front. The Higgs field does not slow things down like friction. It gives them inertia. It gives them resistance to being accelerated. A particle moving at constant speed does not experience any Higgs drag. A particle being shoved, being pushed, that is when the resistance kicks in. Inertia is what we usually call mass. The Higgs coupling is to acceleration, not to velocity, so let us clean this up once and for all. Field versus particle. The Higgs field is the underlying stuff that fills space and gives intrinsic mass to fundamental particles through coupling. The Higgs boson, that particle discovered in 2012, is a quantum ripple in that field, the smallest possible vibration of the Higgs field. It is the smoke that tells you the fire is there. It is not the fire itself. The fire is the field. The discovery of the Higgs boson proved the field exists. The Higgs boson itself weighs about 125 giga-electron volts, a number that itself comes from the curvature of the Higgs field's potential energy, which is a beautiful result but a story for another night. But it also reignited a deeper question that physicists are still chasing. How did the field get its vacuum value? Why 246 giga-electron volts and not 0 or infinity? No one knows. And more important, how did the universe, in its earliest moments, transition to a state where the Higgs field had a non-zero value everywhere? That transition, called Electroweak symmetry breaking, happened when the universe was about a picosecond old. Before that moment, the W and Z bosons that now mediate the weak nuclear force were massless, just like photons. After that moment, they were massive, and the universe gained the property we call mass. Now, let us pull the camera back and ask the next big question. We have established that most mass is energy locked in the gluon field, with a small contribution from the Higgs field's coupling to fundamental particles. So the total mass of any object is just the sum total of all those energies, plus all the kinetic energies of the constituent particles, plus all the binding energies holding atoms together, plus photon and neutrino energies. Every bit of it, every cell of it, can be packaged as a single number called the rest mass. That rest mass, the thing your bathroom scale measures, is energy, always. The question is, why does energy fall? This is the part where Newton stops being useful and Einstein takes over. Isaac Newton's gravitational law worked beautifully. For over 200 years it predicted the orbits of planets, the return of comets, the falling of apples, the tides of oceans. The famous equation, the one with the big G, the masses, the inverse square of the distance, was the most successful formula ever written. But it had a quiet, embarrassing assumption buried inside it. The equation said that two masses, separated by any distance, instantaneously pulled on each other, across the entire universe, with no time delay, with nothing in between carrying the influence. That was fine when everyone thought space was empty. But Einstein showed in 1905 that nothing at all, can travel faster than light. Instantaneous action across any distance is impossible. So Newton's beautiful equation, the one that took humanity to the moon and back, was missing something. A mechanism, a carrier. What is actually pulling? Einstein's answer, the one he published in 1915, was so radical that even his closest friends told him he was out of his mind. Mass does not pull on mass. There is no force. What we call gravity is the geometry of space and time bending in response to energy and matter. An apple falling is not being tugged. It is moving along the straightest possible path through a space that has been curved by the presence of the Earth. A satellite's orbit is not held by a rope. It is moving through curved spacetime. The moon does not see the Earth. The moon just follows its local geometry. The next chapter of the story moves quickly and almost unbelievably. Within weeks of Einstein publishing his final form of the field equations in November 1915, Karl Schwarzschild, a German astronomer serving on the Eastern Front in the First World War, sent Einstein a letter from the trenches containing the first exact solution to those equations. Schwarzschild described the geometry around a single, perfectly spherical, non-rotating mass. He did it while simultaneously working out his own battle calculations under fire. The Schwarzschild solution gave birth to what we now call the Schwarzschild radius, the geometry around a black hole, and ultimately to the entire study of what happens when large amounts of energy are squeezed into a small region of space-time. David Hilbert, the great German mathematician, had been racing Einstein to derive the field equations from a variational principle. Hilbert submitted a variation-based derivation to a Göttingen seminar on November 20, 1915. Einstein submitted a related derivation of his equations on November 25. The credit line on the equations sits with Einstein. The deeper reason why anyone would accept those equations as physical law at all sits partly with Hilbert. But the bottom line is unchanged. Energy curves geometry. Geometry tells energy how to move. Einstein's equation sounds poetic. It is in fact mathematical. Einstein wrote a single equation, actually 10 equations, written as one tensor equation that relates the curvature of spacetime to the energy and momentum contained inside it. That equation is called the Einstein field equation. On the left side, it has the thing that describes how spacetime is curved. On the right side, it has the stress-energy tensor, a thing that looks intimidating, but it just describes all the energy, momentum, pressure, and stress inside whatever region you are measuring. And here is the punchline for tonight. The thing that the equation expects to curve spacetime is not mass. It is energy, momentum, stress. Anything that has energy, anything that has momentum, anything that exerts pressure. Photons curve spacetime, neutrinos curve spacetime, the electromagnetic field inside a magnet curves spacetime. Even a hot cup of tea curves spacetime ever so slightly more than a cold one because it has more energy. So when we say mass creates gravity, the deeper truth is that energy creates gravity. And now that we have understood that mass itself is mostly energy locked in gluon fields, the picture is complete. The reason your coffee cup has weight is energy. The reason that weight causes a pull toward the center of the Earth is that energy curves space-time. Mass, energy, gravity, they are not three separate things. They are one story, told three different ways. Here is a thought experiment that makes the strangeness concrete. Imagine a sealed box, perfectly insulated, sitting on a scale. Inside the box is a battery, a small electric motor, and a flywheel. The motor spins the flywheel up to a high rotational speed. As the flywheel spins faster, the kinetic energy stored in its rotation increases. And, because of E equals mc squared, the mass of that spinning flywheel is greater than the mass of the same flywheel sitting still. The scale, if it were sensitive enough, would register a tiny additional weight. Energy, sitting inside the box, is heavier than no energy. Now, in the real world, a flywheel is heavy enough that you could weigh it precisely, but the energy contribution is so small, on the order of micrograms per gigajoule, that no practical scale would notice. But the principle is exact. There is nothing sloppy about it. If you were to spin the flywheel up to relativistic speeds, where its rim was moving at a meaningful fraction of the speed of light, the additional mass contribution would become clearly measurable. You would see the scale rise. Now take the thought experiment one step further. Imagine the box is not mechanical but nuclear. You have inside a small quantity of a radioactive isotope. The isotope decays, releasing heat, and the heat energy stays trapped inside the box. As the decay progresses, the total mass energy of the box decreases because some of the rest mass of the unstable nuclei has been converted to kinetic energy of the decay products, and that kinetic energy is now bouncing around inside the box as heat. But it traps everything. The total mass energy of the sealed box, by conservation of energy, must remain identical from start to finish. The scale reads the same number. The mass energy that left one form entered another form. The energy is still there. It is just in a different disguise. This is the principle behind so many modern precision measurements. It is why nuclear reactors of submarines can be tracked by sensitive gravimeters, because their internal power densities are slightly changing the way they distort local spacetime. It is why, in principle, a perfect detector could weigh the electromagnetic field inside a charging capacitor and learn something about its energy. A natural objection arises at this point. Everything we have said is about ordinary matter. But the universe also contains antimatter, particles of opposite charge but identical intrinsic properties otherwise. Does antimatter weigh the same? Historically, the answer is yes, with a precision that keeps improving every decade. Paul Dirac in 1928 wrote down the relativistic equation of motion for the electron. To his puzzlement, the equation had not one but two solutions, one with positive energy and one that appeared to give an electron with negative energy. Dirac interpreted the second solution as describing a brand new particle with the same mass as the electron but opposite electric charge, the positron. Carl Anderson at Caltech discovered the positron in 1932 in a cloud chamber photograph of cosmic rays, where it left a telltale curving track in a magnetic field in the wrong direction for a normal electron. Antimatter is real. In 2023, the Alpha G experiment at CERN reported the first direct measurement of the gravitational acceleration of antihydrogen atoms, antimatter counterparts of hydrogen. The experiment was extraordinarily difficult. The team had to make antimatter, hold it in a magnetic trap, drop it, and watch where it went. The result, with fairly wide error bars, fell within one standard deviation of ordinary gravitational acceleration. Antimatter appears to fall the same way ordinary matter does, at least to the precision we have measured. There is no suggestion so far that antimatter antigravitates, that it floats up when released. But this is one of the most important open questions in physics. Any deviation, however small, between the gravitational acceleration of matter and antimatter would imply a violation of an extremely well-tested symmetry called CPT invariance, and it could crack open entirely new ways of thinking about why the universe is made almost entirely of matter, rather than equal parts matter and antimatter. Right now, the evidence is that antimatter falls. We will keep measuring more precisely in the decades ahead. Let us now test this synthesis against something concrete, because physics that does not survive contact with experiment is philosophy. Einstein's geometry idea survived one of the most precise experimental tests in history almost 100 years ago. Mercury's orbit was a small puzzle for centuries. The point where Mercury makes its closest approach to the Sun, called the perihelion, drifts a tiny amount every orbit. Newton's equations could not explain all of it. There was an extra 43 arcseconds per century, a wobble that should not have been there. When Einstein worked through the geometry of curved spacetime around a massive object like the Sun, his equations predicted that Mercury's orbit would precess by exactly 43 arcseconds per century. Not 42, not 44. Exactly, that one number, that one match, was the moment Einstein's wild idea became serious. Gravity as geometry had earned its keep. The next confirmation came in 1919. Sir Arthur Eddington organized 2 expeditions, one to the coast of Africa and one to a Brazilian island, to photograph a total solar eclipse. The idea was to measure the positions of stars whose light had to pass close to the Sun to reach Earth. If Newton's gravity was right, light from those stars would be unaffected by the Sun's mass, because photons were thought to be massless. If Einstein was right, the curved geometry around the Sun would bend the starlight, and the stars would appear slightly shifted from where they normally showed up in the night sky. Eddington's measurements agreed with Einstein. The geometry was real, light bent. The headlines called it the most important scientific result in a generation. The Times of London, a generally reserved paper, broke its usual scientific silence. Then came the modern confirmations. When the global positioning system was first being designed, the engineers had to choose whether to include Einstein's relativity corrections. They did. If they had not, every position calculated by a GPS receiver would drift by about 10 kilometers per day. Your phone knows where you are because the geometry of curved spacetime around Earth is being measured continuously by atomic clocks in orbit. And in 2015, the LIGO Observatory detected gravitational waves for the first time, ripples in the geometry of spacetime itself, caused by 2 black holes spiraling into each other over 1 billion light-years away. The signal arrived at Earth on the 14th of September, 2015, having traveled for something like 1.3 billion years. The black holes had masses of roughly 36 and 29 times the mass of the Sun. When they merged, the geometry around them shook the entire local spacetime by an amount smaller than the width of a proton. And yet, we measured it. The merging black holes released, in those last fractions of a second, more energy, by some estimates 3 solar masses converted to gravitational wave energy, than all the light from all the stars in the visible universe combined. That is what 3 solar masses of gluon field energy can do when it falls into a black hole and rings the local geometry like a bell. That is the experimental credibility of the geometry picture. It is not metaphor, it is engineering. Your phone, your air traffic control, your weather forecasts all rely on the curvature of spacetime being real. And there is one more test, less famous but equally precise, that you should know. In 1964, the American physicist Erwin Shapiro pointed out a 4th distinct consequence of curved geometry. If you bounce a radar signal off a planet that is on the opposite side of the Sun from Earth, the round-trip time should be slightly longer than the flat space prediction, because the path through curved geometry near the Sun is effectively stretched. The shape of space adds about 200 microseconds of round-trip delay to a Mars-bound signal when the Sun is nearly in line with Earth and Mars. The effect is called Shapiro delay. It was confirmed in the 1960s by radar ranging to Mercury and Venus. Then, in 2003, the Cassini spacecraft, while en route to Saturn, performed a precision test of the Shapiro delay as part of its communication with Earth. The geometry of the Sun-Earth Cassini system was nearly perfect for the measurement. Cassini, with Doppler-stabilized radio signals and exquisitely precise atomic clocks, measured the time delay to a precision of about 1 part in 100,000. Einstein's geometry held. Across half a century of better instruments, the prediction held. Curved spacetime is real, not just a beautiful idea, but one of the best measured phenomena in physics. Now, a question that has been gnawing at physicists for a century. If mass is mostly gluon field energy, and that energy curves spacetime, then why does energy curve spacetime? This is the question Einstein himself never fully answered. The Einstein field equation tells you that energy and momentum curve spacetime, and it tells you exactly how much. But it does not tell you why. It does not tell you what spacetime is made of. It does not tell you why energy couples to geometry in this particular way. Einstein called this question, sometimes, the left side of the equation. The right side, with the stress-energy tensor, was well understood by 1915. The left side, the curvature of spacetime itself, was a complete puzzle. It remains a complete puzzle. And here is something worth stressing. Newton's equation worked because Newton did not have to answer why mass pulls on mass. He just noted that it did, summarized the behavior in an equation, and called it a day. Einstein's equation works because Einstein made a similar move. He did not have to answer why energy curves geometry. He just noted that it does. The deeper why is open. The leading candidate for an answer today involves quantum gravity, a physics that does not yet fully exist. The idea is that spacetime itself might not be fundamental. It might emerge from something more basic, perhaps from quantum entanglement, perhaps from the dense mesh of relationships between elementary particles, perhaps from the information content of the underlying quantum fields. There is even a working hypothesis called emergent gravity, which suggests that what we experience as curved spacetime is really a macroscopic pattern generated by the statistical behavior of countless microscopic quantum events. We do not know which, if any, of these ideas is right. Among the more developed answers, three frameworks loom largest. String theory proposes that point-like particles are not really points. Each particle in the standard model is the lowest vibrational mode of a tiny one-dimensional object called a string. Notably, the mathematics of string theory naturally contains a particle of zero mass and spin 2, which is exactly what a graviton, the quantum of gravity, should look like. That is encouraging. The price of admission is that string theory requires extra spatial dimensions beyond our familiar 3, 10, or 11 of them, compactified to scales far smaller than we can probe. Loop quantum gravity takes the opposite approach. Spacetime itself is quantized, built from a discrete network of links smaller than about 10 to the negative 35 meters. Space in this picture comes in grains. The holographic principle, born of black hole thermodynamics in the mid-1970s and now a major organizing idea, suggests that the entire information content of any region of space can be encoded on its boundary. Gravity is then a feature of that boundary encoding. None of these has been experimentally confirmed. Each remains on the frontier. But here is the part where the story closes its loop. Whatever the deep answer turns out to be, we are now certain of three things at once. We are certain that gluon field energy accounts for nearly all the mass of visible matter in the universe. We are certain that energy curves spacetime, and we are certain that the curvature of spacetime is what we experience as gravity. So whether the underlying mechanism is quantum entanglement or something stranger, the chain is unbroken. Energy, field, curvature, falling. Every kilogram of a falling apple, every gravitational wave from a black hole merger, every clock tick on a GPS satellite, every wobble in Mercury's orbit, every Shapiro delay signal from Cassini is part of that chain. Now let us come back finally to the coffee cup. A coffee cup has weight because inside every proton of every atom in its ceramic and in its handle, there is a swirling storm of gluon field energy. That energy is equivalent through E equals mc squared to mass. That mass energy couples to the geometry of spacetime. The Earth has more of that energy than the cup does, and so its geometry is more strongly curved. The cup is moving through Earth's curved geometry along a path that, in the absence of the floor, would lead it to the center of the Earth. The floor stops it. The floor is also energy, also curved geometry. When you stand on the floor, you and the floor are two bundles of curved energy agreeing, for a brief moment in geological time, not to overlap. Your weight, the feeling in your feet, the strain in your knees, is the local geometry of spacetime, refusing to let two bundles of energy occupy the same place at once. There is no force reaching out. There is no invisible rope. There is just two storms of energy, exchanging a moment of contact through a curved shape of the universe. You are not standing on the Earth because gravity is pulling you down. You are standing on the Earth because the energy inside you is curving the space around you, and the Earth is doing the same, and the geometry of those overlapping curvatures is what your inner ear interprets as weight. The atoms in your shoes are pushing against the atoms in the floor because they have nowhere else to go in the geometry they share. That is all. No force reaching out across space. Just two bundles of curving energy, leaning on each other through the shape of the universe. I cannot promise that this picture will feel comforting. It probably will not. There is something unsettling about being told that your weight is the sound of energy singing in invisible fields, and that your standing on the ground is just two geometries agreeing not to pass through one another. But the discomfort is, in my experience, the right kind. It is the kind that comes with waking up a little. The kind that comes with realizing the world is stranger and more elegant than the version you grew up with. That is, I think, the most beautiful thing about physics. When you ask a deep enough question about the most ordinary thing, the answer changes your picture of everything else. And it changes it not into something cold or distant or removed from your life, but into something where you and the floor and the falling rain are all manifestations of one underlying dance of energy and geometry. If you stuck with this for the full 50 minutes, you are exactly the audience I am making these for. If you would like to support what I do, the single highest value thing is to subscribe if you have not already. The second highest is to share this video with one person who would love it. Every share helps a small creator reach someone who would not otherwise find this, and I will see you in the next one.